probability density function, or PDF, was really quite useful if we wanted to visualize what the shape of the probability distribution was, what types of values were more likely than others, where were the peaks, and where were the troughs. Now, for our discussion of continuous random variables, I think the cumulative distribution function, the CDF, capital F of x, is actually even more useful. So back in the discrete world, we use the cumulative distribution function, capital F, to check to see whether or not a proposed probability model looked like a good fit to the data. But it can offer us so much more in the analysis of continuous random variables. We'll still use it to do goodness of fit checks, but we'll also use it for random number generation, to discuss quantiles or percentiles of the distribution, and we'll actually use that as our preferred method for calculating probabilities of finding a continuous random variable in a range. So what is the cumulative distribution function? How do we get it? How do we use it? Let's review. The definition of the CDF, capital F, is actually the same as it was back when we were discussing discrete random variables. So in the discrete world, the way we figured out the cumulative distribution function was to add up the probabilities of observing all values less than or equal to little x. Now, in the continuous realm, we typically do the same sort of calculations, but just replace sums with integrals, areas underneath the curve. And so the CDF, capital F, for a continuous random variable is going to be defined in the same way. It's simply the probability of observing a value of our random variable, capital X, that's less than or equal to a particular value, small x. So the integral from minus infinity, or whatever the lowest possible value is for the random variable, up to little x of the formula that gives us that PDF. So in other words, that CDF, the cumulative distribution function, lets us know how much probability has accumulated up to and including out to that value little x. So graphically, what does this represent? Well, if we draw what our PDF looks like, our probability density function, the CDF is simply the area to the left of little x. So capital F evaluated at little x is the area to the left of little x, that integral from the lowest possible value of our random variable up to and including little x. So computationally, we're just going to be replacing the sum, which we saw in the discrete world, of all values less than or equal to little x, with the integral, the area under the curve, over all values less than or equal to little x. So graphically, what does this CDF, capital F, look like? Well, it's going to be a plot of the probability of observing at most a value of little x as we vary that value of little x over all its possible values. And so it's going to resemble something that usually looks like an S-curve. So obviously for very tiny values of little x, there's not much probability of observing them or something smaller. So the CDF is always going to start out small. And in fact, if there's a lower bound on the smallest possible value of x that can be observed, the CDF is going to be 0 for that value and everything smaller than that. Since it's the probability of observing at most a value of little x, if we can't observe a value of little x or something smaller, obviously that probability is 0. And as the probability accumulates, as we cover more and more values of x that are possible to be seen, the height of that CDF curve is going to increase, and eventually it's going to taper out to 100%. So if there is a hard cap at the largest allowed possible value of x that we can see, the CDF will reach 1 at that point, 100% chance of observing that hard cap, that largest value of x or something smaller, and it'll be 100% for all larger values of x. So for our example that we just saw, that PDF that varied from 1 to 15, what we can see is that those bounds, that 1 to 15, is reflected in our CDF plot. For all values of x that are 1 or something smaller, that CDF is exactly equal to 0. And once we get to that hard cap, that 15, we see that the CDF is equal to 1 for that value and all values that are larger. So let's take a look at the CDF for an example that deals with demand planning. So let's imagine that we have a probability density function, a PDF, that describes the possible demands for a product that we might see in units of thousands. So with this PDF, we can see that it's bimodal. There are 2 peaks. We're relatively likely to observe a value that's near 0.75 or so, And we're even more likely to see a value that's close to about 2.5 or so. So there's actually an equation that describes what the shape of this PDF looks like. It's x times 1 plus the sine of pi x from 0 to 3.5. So let's actually do a really quick review with how we work with PDFs and then talk about, well, what's the CDF, capital F, of this function going to look like? So first thing, we can always take our equation for a shape that we really like and make that into an equation for little f, our PDF, by looking to see what the area underneath the curve currently is. If we throw that into R and use the integrate function just to see, okay, well, what is underneath the area, or what is the area underneath that shape that I like right now? Well, it turns out to be about 6.02. If I just multiply my equation for the shape by the reciprocal of that value, that's going to give me an equation for a valid PDF. It's going to integrate to 1 over the range of possible values of x that I might see. So once I have a valid PDF, I can answer questions about the probability of observing a value inside of a certain range just by asking, well, what fraction of the area under the curve falls inside that range? So in this case, if I want to know the probability of observing a demand between 1.5 and 3, I'm going to take the area underneath the curve of my PDF from 1.5 to 3. I'll throw that into R in this case. I've defined a function that gives us the PDF. So integrating from 1.5 to 3 lets me know that there's about a 73.5% chance of observing a demand of 1.5 to 3. So what I'd like to know, though, is, well, what's the cumulative distribution function going to look like? What's the probability of observing a demand of at most little x? And how does that vary as I change little x from 0 to 3 here? So if I make a plot of that CDF, and we'll talk about how to get that plot shortly, here's what the result actually looks like. So it increases from a height of 0 at the smallest possible value of x to a height of 1 at the largest possible value of x. It's a little bit wavy. That actually reflects how quickly the probability is increasing or accumulating at particular values of x, which values of x are a little bit more likely than others. And if we had this CDF plot, well, we could answer some pretty impactful questions, especially if we had some questions relating to demand planning. So if I had the question, well, what is the probability of observing a demand of at most 2.7? Maybe that's the number of items that I want to have in stock in thousands. Well, the CDF plot lets me know, well, here's that probability. If I just trace up 2.7 to where it hits the curve for that CDF, that lets me know the probability of observing that value or something smaller. So if I wanted to have 2.7 thousand items in stock, and I have my probability demand distribution as given, then I know that there's about a 70% chance that that inventory is going to be able to meet demand. So one thing that I really like using the CDF for actually is to calculate probabilities. So we know how to calculate a probability of getting a value in a certain range. If we just have the formula for little f, the PDF, we just integrate that function from our lower bound to our upper bound in that range. But here's how the CDF, capital F, can offer us a shortcut. So if we had the question, what's the probability that our random variable capital X has at most a value, little a? Well, by definition, that's just capital F evaluated at a, the probability of observing a value at most, little a. And if I had the other question, kind of an undefined upper bound here for my probability question, what's the probability that X is just at least little a? I could use the complement rule. X being at least little a is the opposite of X being at most little a when it comes to continuous quantities. And so I could just take 1 minus capital F evaluated at little a. Now here's where I think it really shines. If I have the more common question of what's the probability of getting a value for my random variable capital X inside of a range, if I have a formula that tells me what capital F is, the CDF, all I need to do is take that formula, plug in the upper value for the range, subtract off the value for capital F when I plug in the lower value for that range, and that'll give me the probability of observing a number inside that range. Now, why does this make sense visually? Well, let's check it out. Here's a plot of the PDF, little f, for a particular random variable. And I might have the question, what's the probability that I observe a value of x somewhere between 7 and 10? Well, I know I could just integrate, the area underneath the curve between 7 and 10 to actually get this, do an integral each time I wanted to answer that question. But here's how that CDF comes into play. Remember, graphically, the CDF evaluated at a value of little x is just the area to the left of little x. So capital F, evaluated at 10 in this case, is all of the area that's been colored blue. So that gives me the probability of observing a value of 10 or something smaller. And if I also consider the probability of observing a value of 7 or smaller, capital F evaluated at 7, well, that's represented graphically here by the diagonal lines. I can see that if I were to essentially subtract off what capital F of 7 was, kind of take away the area to the left of 7 from the area to the left of 10 here, capital F at 10, what I would have left over is exactly the area that corresponds to the question that I was asking. The area between 7 and 10, the probability of observing a value of x between 7 and 10. And so here's one of these key things that we can get out of the cumulative distribution function, capital F of x. If I want to know the probability of observing a value of my random variable capital X inside of a range, I just need to evaluate what capital F is at the upper point of that range, the lower point of that range, and then just subtract the two. That'll always get me the value of the integral if I integrated little f between those two values, so it provides really quite a nice shortcut here. Let's head on over to Wolfram Alpha and see how we could get this for the bimodal demand example. So previously what we had is we had the function x times 1 plus the sine of pi times x, and we were going from x equals 0 to 3.5. This was the shape that we really liked, so we said, okay, let's convert this into a PDF by taking our equation for the shape and multiplying that by the reciprocal of what the area currently is under that shape I like. And the area right now is 6.02368, so let's divide or multiply by the reciprocal of this. Reintegrate just to make sure that the integral is equal to 1. I know I'm dealing with a valid PDF, and so great. So if I did have the question, all right, well, what's the probability of getting a value of the demand, say, between 1 and 3? No problem. I just change my lower and upper limits to reflect the fact that this is the question I now have between 1 and 3, and I get just about 76.9% or so. Now, here's how I can get that same answer just using capital F. All right, well, we've talked about how capital F is just the probability of observing a value of little x or something smaller. So let's take our formula for little f here, the PDF. I'm going to change this so that it's going to be a formula that's written in terms of the variable little t, because little x is actually going to appear in the upper limit of my integration, and I want to keep those two variable names separate. So let's take the formula for our PDF and integrate from the lowest possible value of my random variable that I might observe. Technically, this goes from minus infinity up to little x, but in reality, the lowest possible value for this demand I can see is 0. So let's integrate from 0 to x here. What's the probability of getting, at most, x? And so what this will do is it will give me a formula for what the capital F is, that's CDF. And if I just click on this, I get a nice quick representation of it. And so I can ask, okay, well, let's use capital F to figure out the probability of getting that value in the range. I can copy that, head on over to, say, RStudio. And so once I've transcribed the formula for my function in R syntax, I can define my big F function. And now I can say, hey, what's the probability of getting a value between 1 and 3? Well, that's big F evaluated at 3 minus big F evaluated at 1. So throwing this into R, and I get the 76.97%, which I had seen before. And this is great now because I don't have to do any sort of integration if I have follow-up probability questions. If I want to know the probability of between 1.5 and 2, easy. 2 as the upper limit, 1.5 as the lower limit. It's just really that easy. So if we have a formula for that CDF capital F, answering questions about probabilities of greater than a value, less than a value inside of a range, now all of a sudden becomes really quite easy. So we've discussed how to go from little f, our equation for the PDF, the probability density function, to big F, the cumulative distribution function, capital F of x, well, there's clearly a relationship between those two. What if we want to go the other way around? So what if we actually wanted to recover what little f was, the PDF, from the CDF, capital F? Well, using what we know about integration and the rules of calculus, we can actually relate these two through those two operations that are very popular in calculus, integration and then differentiation. We integrated little f in order to get our formula for capital F, and we're just going to do the opposite of integration, which is differentiation, to take big F and go to little f. And this makes sense. So remember, capital F was letting us know how much probability had accumulated up to that point little x here. Now, if I were to look at the slope of the tangent line of capital F, essentially how quickly that formula was changing at that value of x, that lets me know how quickly the probability was accumulating at that value of little x. Now, the faster the probability is accumulating, the larger the probability of those types of values must be. And so I have this nice relationship between capital F and little f, that little f is really just that instantaneous rate of change, how quickly that probability is accumulating, as the capital F formula lets us know. So to go from capital F to lowercase f, to go from the CDF to the PDF, all we have to do is take a derivative. So once again, what is this derivative? It's really just the slope of the tangent line to a curve at that value of x. And in this case, that holds a special meaning for us because since that capital F, the cumulative distribution function, is how much probability has accumulated up to a value of little x, the derivative, how fast that's changing, lets us know the change in the rate of accumulation of the probability. If the rate of accumulation is very high, we must be in a pocket of values that are relatively likely. If the rate of accumulation is relatively low, the slope of the tangent line is close to 0, that must mean there's not much probability of finding a value of x inside that range. Now, mechanically, we're really just going to worry about, if we have little f, how would we get big F? If we have big F, how do we get little f? We'll use Wolfram Alpha to help us out with this calculus, but there is that nice visual connection that we can see. So for our bimodal demand example, this kind of shines through loud and clear. So in our bimodal demand example, we have the formula for the PDF, the probability density function, plotted in black. We have that peak that's close to 0.5 or so. We have another peak that's close to 2.5 or so. And if we look to see what the CDF is doing, the red curve, the probability of getting a value at most, that value of little x, we see that where the CDF is increasing the quickest, where the slope of that tangent line is the steepest, we find that we're finding peaks in the PDF at those points. The steeper that PDF, the higher the rate of accumulation of probability. That must mean that values near that little x must be relatively likely. So let's get a little bit of practice just translating from little f, the PDF, to capital F, the CDF. So let's imagine that I have a formula for capital F here. That's just 1 minus e raised to the 2 times x squared. And my random variable capital X has possible values little x that are bigger than 0. So let's try to get what little f is, the probability density function, from capital F. What is that PDF going to look like? Well, the two are related just through the derivative procedure. I take the derivative of capital F to get little f, and so I can ask Wolfram Alpha, hey, give me an equation for little f based on my equation for capital F. So I'll say diff, or you can type out derivative if you would like, transcribe the formula that gives you capital F, and then let it know that I'm taking the derivative with respect to x. We know that in probability, we see a lot of other symbols in equations besides just x. We might see lambdas, we might see mu's, we might see sigmas, etc. So we're just cluing Wolfram Alpha in to saying that, hey, this is a function of x, take the derivative with respect to the x variable. And then out will pop out our equation for the PDF, in this case, 4 times e to the minus 2x squared times x. So we could plot that to see, all right, so what does the curve for our probability distribution look like? We're able to very quickly go from capital F to little f. So what about the other way around? What if we had a formula for our PDF? What if we had our shape that we really enjoyed and we wanted to get the formula for capital F? Well, we need to do integration. So to get capital F, the CDF, from little f, the PDF, we need to integrate our formula for the PDF from minus infinity up to little x. Now, whenever we calculate probabilities with PDFs, we always have to ask ourselves when we write down that integral and it has an infinity somewhere, what actually is the lower bound, or what actually is the upper bound? In this case, since we're integrating from minus infinity up to a value of little x, we just have to stop and ask ourselves, okay, but what really is the smallest possible value of x that I need to start out that integral with? So in this case, I'm given that the smallest possible value of x for my PDF is 2. So I'm going to replace that minus infinity in the lower bound with a 2, and I'm going to shoot that over to Wolfram Alpha. Now, here's a trick that I like using. Because we're integrating the formula for the PDF up to that value of little x, we want to know the probability of getting little x or something smaller. It's helpful, but not required, but I think very helpful to write our function for the PDF, transcribe our function for the PDF, not with the variable little x, because that appears in the upper limit of the integral, but instead with a different variable. And I usually like using the variable t. So just to make things clear, hey, we're integrating this function, we're integrating up to a value of little x, I'm going to transcribe my function in terms of the variable little t. So 8 over t cubed dt, throw that into Wolfram Alpha, and out pops the formula for capital F in this case. And true to form, Wolfram Alpha is really written for mathematicians. It's giving us some additional information that we don't really have to care about too much. It's more for the mathematicians, but it's letting us know that this formula, 1 minus 4 over x squared, is going to be valid as long as the real part of x is larger than 0, and if x is not part of the real numbers. That's kind of what that crazy symbol means down in the output of Wolfram Alpha. Now, for us, we're always dealing with real numbers. We don't use imaginary numbers in probability models and business analytics, and so that's just extra information that we can safely just discard. That's for the mathematicians. What capital F can give us in addition is an idea of what the percentiles or the quantiles of a distribution really are. Now, when you were applying for college or when you're applying for a master's program, you sit down and you take your standardized tests. So you might take the ACT, the GRE, the SAT, etc. And what schools typically really are interested in knowing is what your percentile was. What fraction of other test takers scored at your score or something lower. And so this is a question that we often have in business analytics. We'd like to know maybe the 70th percentile of a distribution. What is that value of little x so that if we were to plug in that value of little x into capital F, we get a value of 0.7. In other words, I want that little value of x for which the probability of getting that little x or something smaller is 70%. How do I go about solving for little x in that case? How do I go and solve for these percentiles? So a little bit about notation. What's the difference between a percentile and a quantile? Well, they're really talking about the same quantity. A quantile is just a number that's going to be written between 0 and 1. A percentile is going to be written as that same number, just in percentage terms. So between 0 and 100. So the 0.7 quantile corresponds to the 70th percentile. All right, so visually, what do these percentiles look like? Well, we know that capital F is letting us know the probability of getting a value of at most little x. So if we were to look at a plot of the PDF, the shape of the distribution, that's just the area under the curve to the left of little x. Asking a question like, hey, what's the 70th percentile, is asking, well, what's the value of little x where we find 70% of the area under the curve to the left of x. So in our curve right here, we have values of x going between 0 and 1. If I were to focus in on a value of 0.4, I could ask, well, what percentile is x equal to 0.4? What is the probability of getting that value of little x or something smaller? It's 35.2. So the 35.2 percentile of this distribution would be 0.4. There's a 35.2% chance of getting a value of little x that's 0.4 or something smaller. With the bimodal demand example, well, if I focused in on a value of 2.5, I know that the probability of getting a value of 2.5 or something smaller is 0.5356. So that lets me know that 2.5 must be the 53rd.56th percentile here. So how can I develop a general equation that essentially translates the CDF, capital F, the area up to that value of little x, to percentiles? If I want to ask this question the other way around, I want to know, okay, well, what is the value of x, where there's a 50% chance of observing that value of x or something smaller? Basically the median value of our probability distribution. How do I go about solving for that value of little x? Well, the procedure actually really isn't all that bad. It just requires us to do a bit of algebra. So what we're going to do is write out an equation to give us the quantiles of the distribution. So quantile, just the number between 0 and 1. I want to know what's the value of little x. That is the 0.2 quantile, the 20th percentile. What's the value of little x, where there's a 20% chance of observing that value of little x or something smaller. So our procedure just involves us writing out what the formula is for capital F and then just setting that equal to little q. We're going to give, essentially this equation, the value of little q that interests us. The median would be little q equal to 0.5. The 75th percentile would be little q equal to 0.75. And we want to solve that equation for x. So in very general mathematical terms, the way that we represent this solving for x operation is by taking the inverse of our function capital F. And we're going to write out the solution to the percentiles or the quantiles as x equals f inverse evaluated at q. So give me a value of q, like 0.5 for the median. We'll plug that into the inverse CDF function, and out will pop a value of x that lets me know what the median is, what that quantile is. So similar to when we discussed operations in matrices, that raising it to the -1 isn't the reciprocal operation. That's simply a symbol that lets us know that we're dealing with the inverse of a function. So we have to do some algebra to figure out what that is. So quantiles, the quantile function is what's known as the inverse CDF. Given a number between 0 and 1, a particular quantile, you have a question about what's the value of x that gives that quantile. So I want to know what's the value of the demand so that there's a 90% chance of observing that demand or something smaller. I have a question about the 90th percentile, the 0.9 quantile. What's the value of x where that happens? All right, so let's do an example. Let's see how this algebra works and how we can solve for the quantiles. So what we're going to do is we're going to start out, in this case, with our formula for the PDF, the shape of the probability distribution. And what we have is that little f is equal to 2 times e to the minus 2x. Now, this equation is valid for all values of x that are at least equal to 0. And so let's see how we can get the percentiles, or the quantiles, of this distribution. What's the median value of this distribution? If this described demand, what's the 99th percentile of this distribution? What value of x has a 99% probability of observing about that value or something smaller? So to get the quantiles, we first have to start out with capital F. That's not given to us, so we're going to have to integrate little f appropriately. So capital F is just the integral of our formula for little f from -infinity all the way up to a value of little x. And as soon as we write out that -infinity in the lower limit, we go back to the definition of the PDF and ask, okay, but what's really the smallest possible value of x that I can see? And in this case, it's 0. So my formula for capital F in this case will be the integral from 0 up to little x of my formula for the PDF. And remember my trick, I like writing that formula in terms of the variable t because I already have a little x up in the upper limit of that integral. Wolfram Alpha will still figure it out, but I just like doing that for clarity's sake. So we'll ship this out to Wolfram Alpha. We'll ask Wolfram Alpha, hey, can you integrate 2 times e to the minus 2 times t power from t equal to 0, our actual lower bound, up to a value of little x? And Wolfram Alpha says, sure, I can do that, no problem. And we get a value of 1 minus e to the minus 2x out. So our formula for the CDF, the probability of observing at most a value of little x, is 1 minus e to the minus 2 times x. So we're one step away now from being able to answer questions about percentiles and quantiles. So if I wanted to know at what value of x do I have a 99% chance of observing that value or something smaller, I can do that. I just need to do the inverse CDF operation. So to get those quantiles out, I'm going to write out the equation capital F of x is equal to q. And then I need to do some algebra. I need to solve that equation for x. So in this case, when I write out my equation for capital F, I get the equation 1 minus e raised to the minus 2x is equal to q. And then it's algebra time. Solve that equation for x. So if we're going to do this by hand, well, we just have to isolate this equation so that it reads x equals something, something, something. So we get there by just applying the same mathematical operation to both sides of the equation there, the left side and the right-hand side, until we achieve our goal. So in this case, what we could do is we can add e to the minus 2x to both sides of the equation, and we can subtract q from both sides of the equation as well. That gives me e to the minus 2x equals 1 minus q. I'm going to take the logs, natural logs, of both sides of that equation. So the natural log of e raised to the minus 2x, well, the natural log of the e cancels out, giving me minus 2x, equaling to the natural log of what's on the right-hand side, the log of 1 minus q. And then it's a simple operation. Let's multiply both sides of that equation by minus 1/2, so that the left-hand side of my equation reads x equals, and my right-hand side equals minus 1/2 times the log of 1 minus q. So I'm done. I achieved my goal. I was able to solve that equation for x. I wrote my equation, x equals something, something, something. And that something, 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 what's on the right-hand side of that equal sign, is my equation for the inverse CDF. So that is my equation that gives me the quantiles. So have a quantile in mind, the median, 0.5, plug in 0.5 in that equation, get it out. If I want to know the 99th percentile, plug in a 0.99 into that equation, I get the value of x, for which there's a 99% chance of seeing that value of x or something smaller. Now, you might be a little bit rusty when it comes to doing your algebra skills, and that's fine, because Wolfram Alpha still has you covered. Wolfram Alpha has a great engine for doing algebra. What we can do is simply say, all right, Wolfram Alpha, solve this equation. So solve, transcribe your equation for capital F in terms of x, put an equal sign, put a q, and then add in over the reals. Why over the reals? Well, remember, Wolfram Alpha at its heart is really designed for mathematicians. Real numbers, imaginary numbers, they care about those. We only care about solutions that are fully real. There's nothing imaginary in our analysis, so we're just letting Wolfram Alpha know, hey, just worry about x being a real number here. So it does this, and it comes back with the same equation that we recovered before. Slightly different because it's done a little bit of tricks with the logs here, but we recover that same equation. Throw in the value of q, and out comes the relevant quantile. So another quick example, we've been looking at this bimodal demand distribution, probability distribution, where we have our little f equaling to this equation. That gave us a small peak at around 0.5, a bigger peak at around 2.5. And so we can ask, well, what are the percentiles of this distribution? And here we'll actually run into a little bit of a problem because I made that previous procedure perhaps look a little bit too easy. Because it can go wrong in one of two ways. Number one, it might be the case that even Wolfram Alpha can't come up with an equation for what capital F is equal to. So, for example, let me try doing this. Let me try to integrate the equation 1 over the square root of 2 times pi times e raised to the minus x squared over 2 power from x equals minus infinity to infinity. So why did I pick that particular equation? Well, it just so happens to be a PDF. It integrates to 1 over the entire range of values of x that are possible, any value. But now if I ask the question, well, what's the formula for capital F? Here's my formula for little f here. If I integrate this now, once again, I like writing it in terms of t, from t equal to minus infinity, the lower bound, up to little x, well, Wolfram Alpha will come back with the very peculiar looking expression, well, that's equal to 1/2 times ERF of x over the square root of 2 plus 1. So what is that ERF? Well, ERF is just the abbreviation for another kind of weird looking function, something that we can't just look up what the formula is to, because there actually isn't a nice, easy to write down formula. So we run into the problem that for Wolfram Alpha, we're not actually getting an equation out for what capital F is. And unfortunately, there's a lot of little f's out there, a lot of PDFs, where there's no closed form expression for capital F. Sort of a quick side note, back when I was in college, one of my friends got a chinchilla, and he was trying to come up with a name for the chinchilla. And so I feel like I have a very unique talent for coming up with great pet names. I mean, Cannon, that's the one I named. Eddie named Jackson, not as creative. But Cannon, love that name. Kind of a weird name for a dog. Especially Cannon, because he's such a lump. He just kind of lays around all the time. He's not really that active. But yeah, so I was like, oh, well, you know what? I'm studying probability in one of my classes, and there's this function called the error function, and it's abbreviated ERF. So I proposed ERF for the name of his chinchilla. He went with it, and so ERF lived a long and happy life. But anyway, a lot of little f's out there don't actually have equations that allow us to solve for the capital F, and so sometimes we get a little bit stuck. And in fact, even when we can get an equation for our capital F, sometimes we might not actually be able to do that algebra. But if then we ask the question, well, let's solve capital F of x equal to q for x, and give Wolfram Alpha just a little bit of time to try to figure that out, Wolfram Alpha, disappointingly, is going to come back with something like it doesn't even understand what we're really asking. And this is just Wolfram Alpha's way of saying, yeah, I don't know how to solve this equation, because he can't. It's actually a transcendental equation. This is something that we can't come up with as a solution that's as nice and neat and pretty as x equals ... Notice there's nothing wrong about my syntax here. If I were to just say solve x squared equal to q, Wolfram Alpha is able to handle that no problem. It's just that the equation that we're trying to solve for is just too complicated for Wolfram Alpha. There is no solution, and Wolfram Alpha had trouble identifying that. So what do we actually do in this case if we can't get a formula for capital F, or we can't solve the equation capital F of x equals to q? Well, we can either find those percentiles or quantiles by trial and error, basically say, okay, well, let's define a function in R that gives us our PDF, and then just go between our lowest possible bound and kind of randomly guess what that upper bound is until we find that percentile that we wanted. So if I wanted the median of that bimodal demand distribution, I can change that upper bound just slightly until I get a value of the integral up to that upper bound to be right at about 0.5. That's obviously not very efficient, but Wolfram Alpha will still actually save the day if you have a very specific value of little q in mind. So in this case, what we can do is we can take our formula for the PDF and we can integrate it from the lowest possible value up to x, and then actually solve, then in parentheses have that integrate function, solve that equal to our little value of q that we have in mind, 0.5 in this case for the median, for x. And Wolfram Alpha will go and actually do this with no problem. Now, Wolfram Alpha we'll notice that sometimes there are multiple solutions to that equation, and so you still have to put in a little bit of work to determine which one's the right one, but just put on your thinking cap, use some logic to figure that out. So in this case, it turns out that this equation for the median, the 50th percentile, q equal to 0.5, has two solutions for little x. One's right at about minus 2.35, and one's right at about 2.456. Now, we can automatically eliminate the negative value because we know little x is between 0 and 3.5, and so we have the answer. If I want to know the median demand for that bimodal demand distribution, it's right at about 2.4566. Now, if we wanted to talk about percentiles or quantiles for discrete distributions, the discussion becomes a little bit more complex. And this is why we didn't discuss it back in the previous unit when we were talking about discrete random variables, counts, because it turns out that the percentiles of a discrete distribution aren't unique. The same value of x might serve double duty as two different percentiles, or actually, in reality, a whole range of different percentiles. Why is that the case? Well, here's how the quantile function is defined for a discrete random variable. So for a discrete random variable, this inverse CDF function, the q quantile, is defined to be the smallest value of x for which the cumulative distribution evaluated at x is at least little q. So what does that actually tell us? Well, let's kind of parse this with an example here. Let's imagine that we only have two possible values, 5 and 9. They both occur with equal probability. The 25th percentile, how would we get that? Well, the 25th percentile is the smallest value of x for which the probability of observing that value of x or something smaller is at least 0.25. And so 5 would be the 25th percentile in this case, because it is the smallest value of x such that the probability of that getting that value or something smaller is at least 25%. Probability of getting a 5 or something smaller is 50% in this case. So in reality, 5 is not only the 25th percentile, but it's the 5th percentile, the 6th percentile, the 48th percentile. It's a whole lot of different percentiles. So there's not one unique value of x that is each different percentile with a discrete distribution, and that's why we kind of wisely skipped it. The discussion becomes a lot more complex with it. But one more example, just so you see how this works. One of our notorious distributions is that binomial distribution, counting up the number of successes out of n trials. So maybe we did 50 trials. The probability is 50% of success. I might like to know what's the 27th percentile. What value of x is it so that the probability of observing that value of x or something smaller is 27%. All right, well, unfortunately, there is no value of little x that solves that equation. Big F of little x is equal to 0.7. And so I have to appeal to my definition. If I write out the values of little x of 21, 22, 23, and 24, and the corresponding values of capital F for these, I can use my definition of what the percentiles of a discrete distribution are to answer this question, but it's really not that much fun. So what we do is we look at these values of little x, and what we're looking for is the smallest value of little x, such that capital F, evaluated at that little x, is at least equal to the quantile that we've posed, so 0.27. So where is the smallest value of little x, such that capital F of x is at least 0.27? Well, it looks like 23 is going to be our answer. So the 27th percentile of this binomial distribution is 23, but in reality, there's a 33.6% chance of observing a value of 23 or something smaller. So, 23 is not only the 27th percentile, it's the 28th percentile, it's the 30th percentile, it's the 32nd percentile, it's the 33rd percentile. It's kind of a confusing discussion. So I wanted to bring it up just so that you knew how it was defined, but percentiles, quantiles, of limited use when it comes to discrete random variables, unless they're covering such a huge range so that each percentile is actually associated with a unique value of x.